Hello everyone. In this video, I am explaining 8086 based design problem in which these specifications are given. You have to design 8086 CPU working at 5 megahertz. You have to design it for 32 KB RAM, but only 8 KB device is available. You have to connect 16 KB EEPROM, but only 4 KB is available. So I have explained it in part 1 that whenever we connect memory to 8086, we divide it into two banks, that is even bank and odd bank. So here also we have to divide this into even and odd banks, and this also we have to divide memory into even and odd banks. When we want to select, or whenever 8086 wants to select even bank at a time, it can select either even only one IC at a time. It cannot select multiple ICs at a time. So at a time it will select any one memory IC. When it wants to select even bank, then A0 should go 0. And when it wants to select odd bank, bus enable bar should go 0. This is the standard table which gives a relation between address bus size required and this is memory size. What is relation? N is equals to, this is address bus size, n is equals to 2 raised to power n. This is the standard table calculated by this formula. That means if we have 8 KB device, so 13 address lines are required. If we have 16 KB memory size, so 14 address bus size is required. So here, design 8086 based system. So specifications are given. Operating frequency is 5 megahertz. So what happens to 8086? We connect this 8284 ICs. What this 8284 oscillator IC does, it divides the incoming connected frequency by 3, and then remaining it gives to 8086. Now they have asked to supply 5 megahertz to 8086. So it is going to divide incoming by 5, and hence the applied should be 3 times. So we have to multiply this 5 by 3. So incoming frequency should be 15. So 8284 will divide it by 3, and ultimately 8086 will operate at 5 megahertz of frequency. So these calculations are shown. So part 1 is over. Now we can connect at two locations. We have to connect RAM and EEPROM. Let's assume that we will connect RAM at 0 addresses, that means at the bottom addresses, and EEPROM at the top addresses. So we will start connecting RAM from bottom to top, and we will connect EEPROM from top to bottom. That means from last to previous, and here you will get next addresses. Let's learn how to do this. So we'll first calculate for RAM ICs. So we have decided that starting address of RAM is this. So how much RAM is required? This is given 32 KB. How much is available? 8 KB. So obviously how many ICs of 8 KB will be required? So we will need 4 ICs of 8 KB. As I said, 8086 we divide the memory into two banks, even and odd banks. So here also 4 ICs we have to divide equally. That means there will be 2 odd banks and 2 even banks. This is the RAM IC available with us, that is 8 KB. We know that how to calculate address lines for this. So this is the standard formula and a standard, as I have shown on slide number 3, that there is a standard relation. If we want to connect memory size of 8 KB, remember this 8 KB, this is available. Don't calculate for 32. Many a times students makes a mistake that rather than calculating for 8 KB, they calculate for 32, which is wrong. You should calculate for what is available. So we have 8 KB available. So calculate number of address bus required for available. So 8 KB is equals to 2 raised to power n. So how many address lines are required? N is equal to 13. In 8086, the address bus size is 20 from A0 to A19. This is address bus size of 8086. As I said you earlier that A0 is used for selecting even bank. So we will not use A0 in address mapping. Remember, in 8086, we don't use A0 for address mapping because A0 we use for selecting even bank. Total address lines required are 13, and hence we will select lines from A1 to A13, total 13 lines in the address mapping. So let's see how to do this. So how to perform address mapping, how to draw address mapping table for a RAM IC. So A0 we are using for selecting even bank, and A1 to A13 we are using for address mapping. So first what you have to do, you have to partition it like this, A1 to A13. What is first step? First step is make all A1 to A13 0 and then make all A1 to A13 1. What is the meaning? Meaning is there are intermediate addresses, various combinations of zeros and ones available between. This is the first address and this is last address. Why I made all zeros? Because we have assumed that the first address of RAM IC is 00000. So for that, we have to make it 0. Now for even IC, A0 should be 0. So we will make 0, 0. Now there are remaining address lines A14 to A19. We cannot leave them as it is. We have to put either 0 or 1 or different combinations of zeros and ones. What we should put here? We should make all zeros. Why we are making it all zeros? Because the first address of RAM IC should be all zeros. Now convert it into hexadecimal. Repeat these zeros here also. Same, whatever you write here, repeat it here. So calculate hexadecimal addresses. For calculating hexadecimal addresses, make a group of 444 and let's see what is the first address. The first address is 00000. What is this? This is first address of RAM 1 even bank. And then what is last address? Last address is, you can see here, this is 0, this is 3, 0, 0, 1, 1 is 3, then 1, 1, 1, 1, 1, 1, 1, 1, and this is 1, 1, 1, 0, it is E. So 0, 3, F, F, E, this is last address of RAM 1 even bank. So actually we have to do this for 4 ICs. Okay, because there are 2 even banks, there will be 2 odd banks. As we have calculated, total number of 4 ICs are required. So for 1 IC, we have done the address mapping. Now we will do it for odd bank. For odd bank, this is done. For odd bank, repeat the same procedure, make all zeros, make all ones. And then A14 to A19 also, make all 0. So whatever you are doing here at the first step, repeat it for all 4. If there are 2 ICs, you should repeat the same combination for all 4 steps. And then now we are doing it for odd ICs. So here A0 should not be 0, but it should be 1. So what are the addresses? The addresses are, this is first address of RAM2, which is odd bank. 000. See, this is first address, second address is in odd bank, third address will be in even bank, fourth will be like this. Okay, now what is this? 03FF, last address of RAM2 odd bank. Here you need not to do any calculations, automatically you are getting these addresses. In books, the calculations of these addresses are given, but actually if you do it this way, you need not to calculate these addresses, you will automatically get these addresses. So what we have done for one set of RAM ICs. One set of RAM IC consists of 1 even bank and 1 odd bank. So what is this? This is one set of RAM IC, and for one set of RAM IC, all these A14 to A19 should be similar. Then next is, we will go for second set. For second set, again, we will do for even bank and odd bank. Again, A1 to A13, make all zeros, all ones. Here now we have to go for next address. Here it is all zeros, so here you make it 1. A14 1. So we are going for the next address, next location. You have to go to the next memory location. So 14, you have to make it 1. Okay. So like this, and here again we are doing it for even, so A0 should be 0, 0 for both. So you will get these addresses. What is this? This is first address of RAM3 even bank, and this is last address of RAM3 even bank. You can see as soon as this ends, the next address is here. Then this we have done for RAM3 even bank. Now RAM4 odd bank is second set, second IC is remaining. So again repeat same 0, 0, 0, 0, repeat this combination, and here 0 should be 1, 1, and these are the addresses. These are first address of RAM4, last address of RAM4. So this is second set. Okay, so this is set 1 and set 2. Now for address decoding, you have to choose from anything between A14 to A19. For address decoding, anything from A14 to A19, don't select any address line from A0 to A13. Don't select any address line from A0 to A13 for address decoding. Choose any two address lines from A14 to A19 in which the combination within the set is similar, but across the set is different. So if we select 14 and 15, so here combination of these both lines within the set is same, but here also it is 0, 1, 0, 1, 0, 1, 0, 1. Within the set it is same, but across the set it should be different. Remember, you have to select such address lines in which within the set combination of bits is similar, but across the set it should be different. How it will work? We will use 2:4 decoder in which we will apply two inputs AB, A14 and A15. So A14 and A15, when both are 0, 0, it should select RAM 1 and 2. When it is 0, 1, it should select 3 and 4. So here we are using only Y0 and Y1. Here Y2 and Y3 are also there, but we are not using it. So suppose this is RAM1, RAM2, RAM3, RAM4. The size is 8 KB. So how it works? So A14 and A15. So at 2:4 decoder, when it is both 0, 0, then Y0 will activate. If BH is 0, 0, this is OR gate. OR gate output is CS1. CS1 is RAM2. Here it should select odd bank. Because bus high enable bar is 0. When bus high enable bar is 0, it should select odd. And when A0 is 0, here A0 is 0. Combination of 14 and 15 is same, that is 0, 0. So in that case, it should select even bank like this. These are active lows. Chip select bar. These are bar. These are bar. These are active low. That means when it goes 0, it select that particular IC. At the time, it should select only one IC. Similarly, when 14 is 1 and 15 is 0, then Y1 will be active. And this should select odd bank. And CS4 should select even bank. So this is address decoding circuit. So you have to draw this address decoding circuit at the end of your design. Now we'll do for EEPROM. As I said, RAM we will connect at this address and EEPROM we will connect at the last addresses. Last addresses means FFFFF. Now what is EEPROM required? EEPROM required is 16 KB. EEPROM available is 4 KB. So what you have to do? Number of EEPROM ICs required, 16 divided by 4. It is equals to 4. How many ICs are required? 4. So again we will use 2 even banks and 2 odd. EEPROM available is 4 KB. So according to this formula and according to the standard table, the address lines required are N is equals to 12. Again, this A0 we are using for, as I said, for selecting even bank. So for address mapping, we will use now A1 to A12. Okay. So this is A1 to A12 we are using. Same address mapping, same now. Again, we have divided it from A1 to A12. First, make all A1 to A12 0, 0. This is 1, 1. Here it should be 0. Here it should be 0 because we will be doing for even bank. But now we are connecting it to the last addresses. So last addresses and hence A13 to A19 should be all ones. Why I have taken these all ones? Because I want the last address of the IC should be F, 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 F. That's why. So here it is FE000. So what is FE000? This is first address of from 3 even bank. And then this is FFFE. What is this? This is last address of EEPROM even. Now we have done it for, this is for even bank, even bank. Now we will do it for odd bank. Again, repeat same. All A1 to A12, make it 0. A1 to A12, make it 1. Here, as I said, for all 4 combination, it should be same. So it should be 1, 1, 1, 1, 1, 1. See, these are the addresses. Now here you got. So this, what is this? This is the last address, F, 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 all F. This is what we wanted. And that's why we have started it with this F, 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 F. So it should be F, F, F. This is last address of EEPROM 4 odd bank. Now you have to repeat same. Here again, same. You have to choose A13 and A14 in which combination of this is same. 1, 1. This is for address decoding. Now this is done. Now we will do it for second set. This was for first set. Now we have to go to the previous address because we have started from last address. Now we have to go to previous address. But in RAM, what we did, we started from 0 address, then we have to go to next address. So here we started from last address, so we have to go to previous address. So again, same procedure, A1 to A12, 0, 0, 0, 0 for even bank. Now here I have shown, here I have taken previous address. In RAM IC, we had taken next address. Here we have to take, this is all one, so you have to go to previous address. So for making it previous, you have to make A13, 0. Because before 1, 1, it is 1, 0. So we are going to the previous address, repeat this combination. So this address is C0. This is first address of EEPROM 1 even bank, and this is last address of EEPROM 1 even bank. Then go for second odd bank. Repeat this for all 4 combinations, and these are addresses. Same procedure. So this is previous address. Now again, this is last address of EEPROM 2 odd bank. So here EEPROM 1, EEPROM 2, EEPROM 3, and EEPROM 4. EEPROM 4 has last address. So we have gone previous addresses. Now here again choose A13 and A14. Now these are 2 sets. As I said you, this is one set, this is second set. You have to choose address lines in which within the set the bits are same, but across the set bits should be different. So within the sets bits are same on 13 and 14, 13 and 14, and across the sets it is different. So this is the complete address mapping for RAM IC and EEPROM IC. This is how your address map will look like. Now here, this is address decoding 2:4 decoder for RAM IC, and this is address decoder for EEPROM IC. This is the standard diagram that you have to use. 8086 operating in minimum mode, as I have shown on the second slide. This is standard 8284 IC octal latch. You have to draw this address. Don't consider this. This is 8286 bus trans receiver 3:8 decoder, in which there are 4 address lines: memory write, memory read, input output read, and input output write. How to draw your diagram? This is the standard diagram. This will be same whatever design diagram you are doing. So here from octal latch, you have to draw address lines A0 to A19, and from 8286 bus trans receiver, you have to draw D0 to D15, and then these 4 memory read, memory write, input output read, and input output write. Then RAM 1 and 2. So read write. These are odd bank, even bank, D0, D7, D8, D15. Address lines for RAM IC, we have used A1 to A13. Read and write. Then CS1 and CS2. And then similarly, I have shown this RAM 3. This is RAM 1, 2, RAM 3, and RAM 4. So these are 4 RAM ICs. Similarly, these are EEPROM ICs. This is design diagram, and this is your address decoding diagram. So this is your complete design problem of whatever asked. Thank you very much. Thanks for watching.